Okay, so then let's start with the last talk of the session. So this will be by Frédéric Dupuis on privacy amplification without smoothing. Please go ahead.
Okay, so thank you, Omar, for the introduction. So yeah, I'll talk about privacy simplification and decoupling without smoothing. So let me begin by defining what I mean by these two terms. So first, what is privacy simplification? Well, it's basically a cryptographic task where we assume that we have two players, Alice and Eve, and they share a state here where Alice has a classical part, A, and Eve has a quantum part that depends on A here. And the interpretation is that, let's say, Alice has some sort of would like to generate some sort of secret key that is secret from Eve. So she would like to process her classical state here in order to get something that's uniform and independent from whatever Eve has, right? Eve's some kind of eavesdropper that has some partial information about the classical information, and Alice would like to get something that's perfectly uniform and independent from what Eve has. So if we look at the diagram here, so at the beginning, Alice and Eve are correlated here, and Alice would like to apply some operation here in order to get something that at the end is independent on her, to get a key that's independent and uniform, so that it looks like this here. And what sort of operation can she apply to achieve this? Well, it's going to be choose a random hash function from a suitable family of hash functions, and then apply it to A, and then she gets a C out. So we can model this operation like this here. And then what we want at the end is something that's, well, close to the ideal case here. So the real thing, so the hash function applied to A is close in trace distance to the ideal case here. And so close would be so small here. And what do I mean by small? Well, it should depend on two things. It should depend on, first of all, the size of the C system. So how many secret bits is she trying to get out of it? So it should depend on so the log of the dimension of C here. And it should also depend on how much information Eve had about A in the first place. So there should be some kind of information measure of how much information there is in A given E here. So it should depend on something like this here. So there's going to be an information measure. We'll see that we have to figure out which one. And should be something like this. And it's going to be some sort of exponential bound here. So there's going to be, the bound should look something like this. So this is what we're hoping for here. And of course, there's an important case here where when rho is an IID state, so when A actually consists of n copies of the same distributions, and Eve also has n copies of the same state. But the whole state looks like tau AE tensor n. So we'd like to be able to deal with this easily, because that's either an important case by itself, or many important cases, like in quantum cryptography, can be reduced to it fairly easily. Decoupling is it's more or less the same sort of tasks, but where where everything is quantum. So where A is also quantum and E is still quantum. So now, instead of having a hash function, what we do is Alice is going to choose a quantum channel from a suitable family of quantum channels, and then apply RH to A to get a uniform quantum system out that is independent from Eve's system. And again, everything looks essentially the same, modulo this fact. Again, success is again like the expectation over the choice of channel of the trace distance between the real case, so what really comes out of this whole thing, and the ideal case where we have a perfect uniform system tensored with something independent at Eve. And again, small is again in the same sense. It should depend on two things: how many qubits we hope to get out, so the dimension of C, and a measure of the amount of information there was in rho AE in the first place. So again, some measure of information in A given E. And So this can be used to prove a wide range of achievability results in quantum Shannon theory via Ullmann's theorem. The idea being that once we've established that two systems are essentially independent, this means that if there's a purification out there, the purifying system has perfect correlations with both of these systems. And then the idea is that we'd, for example, in channel coding, would like to ensure that whatever comes out at Bob's end is completely, or like the purification of what we're trying to send is completely independent from the channel environment, which means that the receiver who holds the purification now has perfect correlation with the purification of what we're trying to send. So there's all kinds of games we can play here once we have a theorem that looks like this. I'm not going to discuss this point further here. So now I'd like to get into this this information measure business. So like I said, we need some way of measuring the amount of information that was in A given E. And there are three measures here that are relevant in this talk. The first one is the von Neumann entropy that we all know and love. So it has all kinds of nice properties, right? So it has all like a bunch of chain rules. It's basically the right quantity for pretty much anything IID. Pretty like whenever there's an IID task, the von Neumann entropy is going to be the right measure to look at. And for this task, so this is a one-shot task. It turns out to be too good to be true in general, in the sense that if we go back to what we'd like to achieve here, if we were to plug in the von Neumann entropy here as our information measure, this would yield a theorem that's just too good to be true, basically. So we have to do something else in the general case. So what can we do in that more general case? Well, so there are these two measures that I'm going to discuss. So the first one is the min entropy. So this is again something that's fairly well understood. It's defined like this here. So it's basically the min entropy of A given E is essentially the probability of guessing A by measuring E by the best possible strategy. And so this has also all kinds of nice properties. In particular, it's a semi-definite program, and it's quite well understood. And we'll see that in most cases we need to do something called smoothing to make this thing useful. And we'll see this very soon. The next information measure that's relevant here is the sandwiched Rényi entropy. So this is something that's a little bit less known. It's defined like this here, but the exact expression is not really important here for us. What is important is that it's parameterized by a real parameter here. So there's a parameter alpha that makes sense between 1/2 and infinity, including infinity, and it generalizes both of these above quantities. So at alpha equals 1, it's the von Neumann entropy. So when we take the limit of this expression as alpha tends to 1, we recover the von Neumann entropy. At infinity, again, taking the limit of this expression as alpha goes to infinity, we recover the min entropy. And then alpha between those two quantities interpolates smoothly between those two cases. So this was more recently defined, and we're starting to understand it better. And we'll see that basically it's a very good expression to use in the private simplification and decoupling problem, as we'll see. So what is known about the private simplification? So there's a theorem by Renner from back in 2005. That's basically the plain version of private simplification, from which we can derive a bunch of other ones. But this is like the proof of private simplification gives us the following result. So here on the left-hand side, we have the expression we'd like to bound here, and it's given in terms of this. So we have 2 to the 1/2 times the size of C. As we said, this is expected. And then here, the information measure that we have is the sandwiched Rényi entropy at alpha equals 2. So this is what we get. The problem with applying this directly to problems of interest is that it usually doesn't give very good bounds. For example, even for the IID case, we have that H2 is in general strictly less than the von Neumann entropy. And in the IID case, we really expect the von Neumann entropy to be the right quantity. So this is already a problem. Like we don't get a very good bound from this from the start. So what do we do to deal with this is something called smoothing. So the first thing we do is instead of using the 2 entropy, we use the min entropy, which is a lower bound on the 2 entropy. So we might lose something, but the bound is still true if we just replace H2 by H min here. It makes the bound slightly worse. And what we gain by making the bound slightly worse in this way is that we move to an entropy that's better understood. And in particular, we can do the following trick. So we can define the epsilon smooth min entropy, and it's basically defined as the min entropy. So the smooth min entropy of a state rho is defined as the best smooth min entropy of all the states in an epsilon ball around rho. So this is a ball that's epsilon here around it. It's measured in something called the purified distance. So it's some distant measure that's not really important for the stock. But yeah, we basically optimize the min entropy in a small ball around the true state. And then what we get is something that looks like this. Instead of Renner's theorem, we get something where the basic bound here is the same as we had before, but with the smooth min entropy instead of the 2 entropy here. And then from the smoothing, we have to do a triangle inequality argument, which means that we get this epsilon parameter added on here. That's just some additive error. And then what this buys us by doing this is that in particular, at least it works in the IID case and in other cases of interest as well. Because it turns out that H min epsilon is very close to n times the von Neumann entropy of a state when the state is IID. And I'm going to go through a very high level sketch of this proof that H min epsilon is more or less the von Neumann entropy in this case, because this is actually relevant to the stock. So this is known as the fully quantum asymptotic equipartition property, and it states the following. Right? So that H min of epsilon of A1 to n given E1 to n for some IID state is at least n times the von Neumann entropy. So this is what we want in this case, minus something that's in O of square root of n. And the core of the proof of this fact goes as follows. So it's done in 2 steps. So first we have a bound that converts between that converts from H min epsilon to H alpha. So this is the again our sandwiched alpha entropy. At some alpha here, and then we pay a penalty term that looks like this here. So it depends on epsilon and it depends on alpha. Now that we've done this here, the first term is additive. So when we have H alpha of an IID state, it's n times the H alpha of one copy of the state. And then we do another conversion step from H alpha to H. So we get to our von Neumann entropy. And then we again have to pay a price. And the price this time is something that depends on alpha, depends on n, and v here is some constant that depends on the size of one of these copies of the state. So like the dimension of alpha, of A, essentially. And then to recover our theorem here and get this order square root of n, all that's left to do is to choose an alpha. So here alpha is a free parameter in our derivation. And then if we pick alpha is equal to 1 plus something that's O of order of n, right? So O of 1 over square root of n, something of n here, something like this, then we get our theorem. And for those of you who are into QKD security proofs is something called the entropy accumulation theorem that works in essentially the same way. So at the core of the proof at a high level is more or less the same, except that, well, things are a bit more complicated in some of these steps. Like this here is not so direct, but at the core of it, this is what's going on. And what I'm interested in doing here is basically to cut out the min entropy. So I'd like to do everything in terms of the sandwiched entropy instead of the min entropy, and then only have to do that last step here and skip the first one. And we'll see that we get cleaner results at the end. So the main result is the following. So so basically we can get the same as Renner's result, except that instead of having H2 here, we're going to have H alpha for alpha between 1 and 2. And then the point is that here in the previous proof, we were choosing alpha being just above 1. And here in this theorem, this lets us choose this alpha directly, right? We can choose an alpha that's just a little bit above 1 and plug it in directly into the privacy amplification achievability results. And then we're not going to have to do this whole song and dance about the min entropy and then smoothing and then all of this. Like, we could just do this last part of the proof here, and then we'd have a bound in terms of H alpha, and then choose an alpha that's suitably close to 1 directly in the privacy amplification result. And then everything else is more or less the same. And then we have this prefactor here that also depends on alpha. And this here is less than or equal to 2, right? So this is not so important. So this is the main result. So what is known about in this direction? So this is not the first result in this of this flavor. So in particular, the fully classical case. So the case where A and E are both. Oh yeah, maybe I should mention first. So I've been talking about private simplification, and in terms of decoupling, the picture is essentially the same, right? So pretty much everything I've said so far is also true when A is quantum, and we're doing decoupling rather than private simplification. So this is true for both the classical and the quantum case. Okay, so back to previous work. So in the fully classical case, so when both A and E are classical, this result is known, basically. So this was done by Masahito Hayashi in this paper here, and the result is basically the same, right? So this, except for the prefactor that's 3 here instead of 2, and everything else is basically the same. Then in the CQ case, so this is basically the quantum private simplification setting where A is classical and E now, so Eve's system is quantum. Then Hayashi in this other paper also has a result that looks like this. So there are 2 differences between this and our main result. So the first one, which is not so important, is the fact that here we use the PET Rényi entropy rather than the sandwiched Rényi entropy. So it's a slightly different definition of the Rényi entropy, which in general is slightly bigger. So it's a slightly worse result, but if we take the limit as alpha goes to 1, usually it's not a big deal. It's going to be essentially the same. Qualitatively, it's going to give more or less the same answers. The bigger difference is this term here. So we have a term in terms of the number of distinct eigenvalues in the original state. When we're applying this theorem to an IID state, this is not a big deal because the number of distinct eigenvalues in an IID state grows polynomially in N, which means that here we would get a prefactor that's polynomial in N, and here we get something that's the main bound is exponential in N, so it just goes away. There's also a version involving the ratio between the largest and smallest eigenvalues. This is also not a big deal in the IID case, but in the general case, it is a big deal because it's not so easy to in general we don't have a bound on these 2 quantities. So to deal with this, we'd have to somehow go back to smoothing, for example, to be able to control this, and then we basically go back to something that's very close to the smooth min entropy approach. And then in the fully quantum case, in the decoupling case, there's also a similar bound that is known. So this is by Naresh Sharma in this paper. And again, it's the same sort of result, but where there's a term where involving the number of distinct eigenvalues. So again, this is good for the IID case and not so good in the general case. So here our main result basically solves this problem about the extra term that can't be bounded easily in the non-IID case, so that it can be applied, for example, in QKD settings, like in the entropy accumulation theorem, for example, which are sort of IID-like but not actually IID. And what this sort of result lets us do, if we go back to the core of the proof that I had a bit earlier, where if I go back to it, so we had this this proof that in the IID case everything goes well, so we convert h min epsilon to h. Well, in this case we can just go from here to here, because now all we need in the like in the private simplification bound or the decoupling bound is a bound on h alpha. So we don't need to care about the h min, so we only need to do this last step in it to get the bound we want in terms of the von Neumann entropy. So here, the score of the proof becomes something that just looks like this here. So it's the last step. And then what we have to do is optimize over alpha. The trade-off is that, so there's an alpha that shows up in this part of the bound here, and there's also an alpha in this prefactor of the exponent here. And then once we optimize this over alpha, we can get an error exponent here that looks like this, for example. So we're going to have the actual von Neumann entropy of it and the difference with the rate, and then divide by this v term here squared, and then we get this as our error exponent. So we can get an error exponents quite easily using this approach. And I guess I don't really have time to go into this here, but yeah, so this can be plugged in directly to something to the entropy accumulation theorem. That's useful, for example, for getting device-independent bounds in QKD protocols. And I guess I don't really have time to go into it. The point about this theorem is that it's sufficiently close to IID that the answer that we expect is the von Neumann entropy. The core of the proof again looks basically the same as in the IID case, but it's not an actual IID theorem, because there's an adversary that can behave however they want in the middle of the protocol. So it's not true that every round is exactly the same because of the behavior of the adversary. And then if we do this, then we get a nice bound in a setting that looks a bit like the IQKD. So this was a toy setting that looks like the IQKD. I'm not going to really have time to go into it. For those of you that are into this stuff, one of the interesting features is that the probability of the observed statistics here enters the bound in a much more natural way than it did in the original EAT paper. We don't have to assume a bound on it and then do a case analysis if it's bigger or less than this bound. But yeah, I don't have time to go into it. So a few words about the proof method for this main theorem. So the main technique used is norm interpolation. So there's something called the Ries-Thorin interpolation theorem. So it's a theorem that lets you interpolate between two norms. So if you have two Schatten P norms, so one with parameter P0 and one with parameter P1, you can get a bound on the P theta norm where theta is between P0 and P1 in the sense here, and then you get an interpolation theorem like this. We don't actually use this theorem directly, but we use the same proof method. So there's the Adamov three-line theorem that's used to prove this, and we use that directly in our proof. But the point is, so we can write the sandwich-Renyi entropy in terms of a Schatten P norm like this here, and then we can use a similar technique to Ries-Thorin to interpolate between two two results. So the first result is this is Renan's original proof with alpha equals 2 here. So if we plug in so this is our main result with alpha equals 2, we get exactly Renan's original theorem. And the second thing we interpolate with is alpha equals 1. And if we plug in alpha equals 1 into our main theorem, we just get a very complicated way to write 2. So we basically get the interpolation between the original theorem by Renan and a trivial bound of 2 here. And of course, 2 is just, we get nothing here, right? Like if we have, this is the trace distance between two quantum states, which is at most 2, right? So this gives us nothing. And then we get our main result by doing this. So it's basically just the interpolation between 2 and 1 of Renan's result. And this is why our theorem is limited to alpha between 1 and 2. It'd be nice to have it above 2, but I don't know how to prove this. But it's also not the most interesting case because as I said, the main case where we want to apply it is at alpha just above 1. Okay, so I guess I'm at the end of my talk. So a few open problems in this direction. So the first one is, well, can we do this to all of one-shot quantum information theory? So can we reunify all of the achievability theorems in quantum information theory? So the fact that this works for decoupling gets us part of the way there. So like I said, the decoupling part of this paper it implies a bunch of other coding theorems, but I don't think they give us very, very good bounds in the sense that we end up getting results in terms of linear combinations of Rényi entropies, and those are probably not the right quantities to look at. So I think we need more specialized theorems in most cases of interest. And a second thing it lets us do is deal with the something called the simultaneous smoothing problem. So this is in multi-user information theory problems where we end up with multiple smooth quantities in the answer, and often what we want is to find a single state that achieves the smoothing in all of these problems, right? So if you recall that the smoothing problem was you find the best state somewhere in the bound around the true state, and if we have multiple smoothing problems, is there a state that achieves a good bound on all of these problems at the same time? So it's not always obvious. And the way this would solve the problem is that, well, we get rid of smoothing altogether, so the problem disappears if we do multi-user information theory problems this way. Is that we just get an answer in terms of Rényi entropies, no smoothing is needed, so that the problem just disappears. So yeah, that's the end of my talk, and thanks for coming.
Okay, so thanks a lot, Fred, for this talk. Are there any questions? Maybe I start with one. So, so concerning this privacy amplification, so I think your result applies if your family of functions is too universal or is maybe close to too universal. Is there a chance that it works for any valid extractor? So, for example, for these Trevisan extractors, it's not of this form. So, could we apply this bound?
I guess no is the answer. So that's definitely a drawback of this approach, and I don't think it's easy to fix this problem. And the reason is that if you look at the definition of an extractor, the min entropy is basically baked into the definition. So I mean, by definition, you need a bound on the min entropy to be able to apply an extractor. So unless your extractor has more, unless you know more about the extractor than just the plain definition of an extractor, I don't think there's anything that you can do except have something that works with the min entropy. So yeah.
Any other quick questions? Okay, if not, let's thank all the speakers of the session again.